I want you to try and imagine, just for a second, the internet without a boss.
Right.
Like there is no CEO.
No central command at all.
Exactly. No master switch you can just pull to turn off half the web. But, back in June of 2021, a single customer of a massive cloud computing company updated their service configuration.
Just a routine maintenance thing, right?
Totally valid change.
Yeah.
But within literally minutes, Amazon, Reddit, Twitch, Spotify, I mean, even the entire UK government website, they just vanished. Gone.
Oh, yeah, I remember that.
You'd open your browser, hit enter, and just stare at an error page. And it really makes you realize that the internet relies on this invisible, kind of unglamorous infrastructure that, well, when it hiccups, it breaks the modern world.
It absolutely shatters the illusion we all kind of walk around with. We treat the internet like a natural force, like gravity or water pressure.
You turn the tap, and data flows.
Right. But beneath that surface, it is a wildly fragile ecosystem of protocols. And I mean, most of these were designed in the 70s and 80s for this tiny, tiny network of trusting academics.
Definitely not for what we use it for now.
No, they were never meant to handle like global commerce or 4K video streaming or, nation-state cyber attacks.
So our mission for this deep dive is to really explore that hidden load-bearing infrastructure, the systems running the application layer that you use every single day while being honestly completely oblivious to the chaos happening under the hood.
It's fascinating stuff.
We're going to look at how names turn into mathematical addresses, how asynchronous messages actually traverse the globe, how servers mathematically agree on what time it is, and, my favorite, how massive streaming files actually manage to cheat the physical speed of light.
And as we dig into these, totally disparate systems, this grand unifying theory emerges. Every single technology we're going to talk about today solves the exact same brutal problem.
Which is global coordination without a central authority.
Exactly. If you want a system to survive at planetary scale, you cannot have a central database. It just doesn't work. You solve it using two core mechanisms. First is hierarchy.
Right, breaking things down.
Yeah, you aggressively partition the workload so that basically no single machine on Earth needs to know the entire map.
Because if a machine has to know everything, it becomes a catastrophic bottleneck.
Yeah.
I mean, if that one machine melts, the planet goes offline.
Precisely. Which is why the second mechanism is arguably even more vital, and that's caching.
Oh, caching is huge.
You take the answers you've recently discovered, and you replicate them physically close to the user asking the question. So you're basically trading perfect, to the millisecond consistency for raw speed and survivability.
So hierarchy divides the universe, and caching remembers the local neighborhood.
That is exactly the way to look at it.
Let's see that unifying theory in action then. Starting at the very millisecond you initiate any action online. Because, well, before a single pixel loads on your screen, your browser has to figure out where a human-readable name, like example.com, actually lives on the physical network.
Right, the DNS lookup.
Yeah. And I know people call the domain name system or DNS, the phone book of the internet. But I gotta be honest, that metaphor always felt broken to me.
Oh, it's a terrible metaphor.
Right. A phone book is a single centralized list published by one company. If DNS were built like that, it would have collapsed decades ago.
It really would have. It is much more accurate to visualize DNS as this massive decentralized graph. It's a tree structure that grows upside down.
Okay, an upside-down tree.
Yeah, and at the very top of this tree is the root. But interestingly, the root doesn't actually have a name. It is an empty label. It's a literal invisible dot at the end of every domain name that your browser just hides from you.
Wait, really? So when I type example.com, there's secretly a dot at the end, like example.com ...
Yes, formally, the fully qualified domain name ends with that dot. That silent dot represents the root of the entire global hierarchy.
That is wild. I never knew that.
Yeah, and beneath that silent root, the tree branches out into the top-level domains, the TLDs. The .coms, .orgs, .jp for Japan, .uk for the UK.
Okay, that makes sense.
And beneath those are the second-level domains. These are the actual organizational names. It's like example. So when your computer reads a domain name, it is actually reading a routing path from the bottom leaf of that tree all the way back up to the root, right to left.
The brilliance here really seems to be the concept of zone delegation. It creates this hard boundary in the graph, right?
Absolutely.
Because the root servers, these highly critical machines scattered globally, they don't actually know the IP address of example.com. And they don't care. Their only job is to point to the servers that manage .com.
That boundary is the seam in the distributed database.
Huh.
The root delegates authority to the .com servers. Then you query the .com servers. But they also do not know the IP address of the specific web server you want.
Right, they just pass the buck again.
Exactly. They just look at their records and say, well, we delegate example.com to this specific set of authoritative servers managed by that company. It is only when you finally reach those specific authoritative servers that you get the actual IP address.
It is like the ultimate delegation of responsibility. An organization can change its hosting provider, they can swap out thousands of IP addresses, spin up new subdomains, all without ever having to call some central internet committee to update a master ledger.
It's beautifully scalable.
But wait, if I type a URL, my laptop isn't actually doing all that interrogation, right?
Yeah.
My laptop isn't walking the global tree from root to leaf.
No. Your laptop is acting as a client making what's called a recursive query. It basically hands the entire problem to a recursive resolver.
Which is what, exactly?
Usually a server run by your internet service provider or maybe a public one like Cloudflare or Google. Your laptop just says, hey, I want the final IP address for example.com, and I refuse to do any of the legwork. Go fetch.
I always think of the recursive query like dealing with a really high-end hotel concierge.
Oh, I like that.
Yeah, you ask them for opening night opera tickets, and you ask exactly once. The concierge is the one who has to make the phone calls, talk to the box office, negotiate with the courier, and then just come back to you with the tickets in hand.
That's a fitting analogy because that concierge, the recursive resolver, has to use an entirely different method to talk to the rest of the internet. It uses iterative queries.
Iterative, right, so it does the walk-in.
Yeah, it goes to the root and asks for example.com. The root replies, I don't know, but here are the .com servers. Then the resolver iterates, asking the .com server. It gets referred again. The resolver is doing all the heavy lifting, walking the global hierarchy step by step until it corners the authoritative answer.
But this design still sounds like it would accidentally take down the internet, like a massive DDoS attack on the root servers. Well, if every time anyone on Earth clicked a link, a resolver had to ask the root for directions to .com, the root would melt under billions of queries per second, wouldn't it?
It absolutely would. Which brings us to the second half of the grand unifying theory, which is caching.
Right.
Every single referral the resolver receives comes with a time to live, a TTL. This is a cryptographic expiration timer. When the root tells your local resolver where the .com servers live, it attaches a TTL of, say, 2 days.
Okay, so it remembers it.
Exactly. For the next 48 hours, your local resolver will never bother the root servers for any .com address. It caches the structural map.
That creates a massive protective umbrella then. The root servers are shielded because the billions of devices at the edge are just relying on the memory of their local resolvers.
Yeah, it saves the system from collapsing.
But doesn't that introduce a massive vulnerability in your operational workflow? Like if caching saves the internet, why don't I just set the TTL on my company's authoritative website record to a full year? I'd get incredible speed in zero DNS query load on my servers.
You definitely would. Right up until the day your physical server catches fire and you need to migrate to a backup data center with a new IP address.
Yeah.
If you forget to lower your TTL down to, say, 5 minutes a few days before you make that migration, you fall into the migration trap.
Because the entire planet's recursive resolvers have your old IP address locked in their memory for a year.
They do. And you can update your authoritative server all you want. The authoritative server will scream the new IP address into the void, but no one will hear it.
Because no recursive resolver will bother asking.
Exactly. They already have an unexpired answer in their cache, so your users will be routed to a dead IP address for months. And there is no central override switch. You simply have to wait for the local caches to decay. The TTL is this brutal economic trade-off between network efficiency and data consistency.
That is a terrifying operational mistake to make, just accidentally taking your own company offline for months.
It happens more often than you'd think.
But there is a much darker vulnerability in this system, right? If the local resolver's memory is what dictates reality for the user, what happens if someone injects a hallucination into that memory?
You're referring to cache poisoning. It's basically the foundational flaw of early DNS. Remember, this protocol was built on cleartext UDP, User Datagram Protocol.
Which means it's connectionless.
Connectionless, unencrypted, and historically entirely unauthenticated.
It's just throwing digital envelopes over a wall and hoping someone catches them.
Basically, yeah.
So when the recursive resolver sends out an iterative query asking for an IP address, it attaches this tiny 16-bit transaction ID number to the question, right? And then it just waits for an answer envelope to come back with that exact same 16-bit number.
Right, and the vulnerability which was famously exposed by Dan Kaminsky in 2008 is that an attacker doesn't actually need to hack the server, they just need to win a race.
A race against the real server.
Exactly. The attacker forces your resolver to ask the authoritative server for a domain name. And while the true server is processing the request, the attacker floods your resolver with thousands of fake answer packets, just guessing the 16-bit transaction ID.
And since 16 bits only gives you, what, 65,000 possible numbers?
Roughly.
If the attacker pumps enough packets fast enough, they will easily guess the right ID before the legitimate answer arrives.
And the resolver blindly accepts the first answer that matches the ID. It writes the attacker's fake IP address into its cache alongside the TTL.
And the cache is now poisoned.
Yep. For the next 24 hours, anyone on your entire ISP who asks for, say, your bank's website will be silently, flawlessly routed to a perfect clone controlled by a hacker. The browser's URL bar looks correct. The request looks normal. But the underlying map has been warped.
So you have this fundamental flaw in the architecture. And you can't just change UDP to use, like, 64-bit transaction IDs, because that would require ripping out the legacy infrastructure of the entire internet simultaneously.
Which is impossible.
Right, so you have to bolt security on top of the existing structure.
And the solution they bolted on is this cryptographic marvel called DNS-SEC. It retrofits origin authentication and data integrity onto the cleartext protocol by utilizing the one thing DNS already has, which is the hierarchy.
Right. If you can't trust the packet itself, you build a chain of trust that mirrors the delegation tree we just talked about.
Exactly. With DNS-SEC, the owner of example.com uses a private cryptographic key to digitally sign their IP address records. They publish the public key right there in the DNS zone. Now, the resolver can do the math to prove the IP address hasn't been tampered with.
But wait, if I'm an attacker, I can just poison the cache with a fake IP address and my own fake public key and just sign it myself. How does the resolver know the public key is actually yours?
This is where the hierarchy saves the day. How do you trust the example.com key? Because the parent zone.com signs a mathematical hash of it.
Okay, I see.
And how do you trust the .com key? Because the root zone signs a hash of that. And the root key itself is a widely known trust anchor that's literally baked into the software of every resolver on Earth.
Oh, wow.
So when the resolver gets an answer, it walks the cryptographic signatures all the way back up to the root. Unless the attacker can somehow steal the private keys of the .com registry, which they can't be, their forged answers will fail the math check and be dropped.
That is brilliant. It secures the map completely. It stops cache poisoning dead. But let's look at the gaping hole DNS-ACC intentionally leaves open, which is privacy.
Yes.
Because the signatures proved the data wasn't altered, but the queries themselves are still flying across the network in cleartext UDP.
Right. DNS-SEC provides integrity. It does not provide confidentiality. So your local coffee shop, Wi-Fi, your internet service provider, or literally anyone sitting on the physical network path can see every single domain name you request.
They might not see the specific web page you're on, right? Because HTTPS encrypts the traffic between you and the web server.
Right.
But they see the DNS query.
They see the domain, they know exactly which doors you're knocking on, they can build a devastatingly accurate behavioral profile of you just by logging your DNS lookups.
And to plug that leak, engineers built DNS over HTTPS, or DOH, and DNS over TLS, DOT. They finally wrapped the DNS query in an encrypted tunnel.
Which sounds great on paper.
It does. But here's my issue with DH. It doesn't just encrypt the query, it completely alters the routing architecture of the internet. By default, my laptop asks my local operating system to handle DNS, which usually asks my local ISP. But with DH, applications like web browsers, Chrome, Firefox, they started ignoring the operating system entirely.
Yeah, they bypass it completely.
They take the query, encrypt it, and fire it off to a centralized public resolver, like Cloudflare or Google.
You hit on a massive governance tussle. DOH is a profound privacy upgrade against local network snooping. Your ISP goes blind. But the trade-off is centralization. We are taking a wonderfully decentralized global capability and funneling the browsing history of billions of users into the data centers of 3 or 4 massive tech conglomerates.
Not only that, it completely breaks enterprise security. Like, if I'm running an IT department, I rely on the corporate DNS resolver to block employees from accidentally clicking on known malware domains.
Of course.
If their web browser quietly tunnels all DNS queries directly to a third-party tech giant over an encrypted HTTPS connection, my corporate firewall can't see it, it can't inspect it, and it can't block the malware. You're trading ISP snooping for enterprise network blindness.
It is the classic architectural trade-off. We patch a security flaw, and in doing so, we shift power. We are actively centralizing the edge of the internet to protect it from the middle. But, this naming layer, this DNS architecture, is not just about translating web addresses.
Right.
It is the invisible backbone of a completely different paradigm of communication.
Email.
Email. It is older than the web, it survives literally every attempt to replace it, and it relies on an entirely different physical architecture.
Because when you browse the web, it is a synchronous connection, right? Your browser and the web server must hold a continuous, real-time connection. If either party drops offline for like 3 seconds, the connection terminates.
Exactly. But email is deeply asynchronous. It is a store and forward system. When you send an email, the architecture fundamentally assumes the recipient might be offline.
Their phone could be dead.
Their server could be undergoing maintenance, a submarine cable could be severed, it doesn't matter. The system is built to cache the message at intermediary nodes and ruthlessly retry delivery until it succeeds.
To map that journey, we really have to look at the protocol split. When you hit send on your phone, you are using the mail user agent, the MUA.
Right, the app itself.
Yeah, and it connects to your provider's server, which is the mail submission agent, or MSA. This is usually an encrypted, highly authenticated handshake. You prove you are a paying customer, and the provider takes custody of the message.
And now the provider acts as the mail transfer agent, the MTA, and has to route this message across the open internet. And this is where it asks DNS for directions, but it doesn't ask for an IP address.
What does it ask for?
It specifically asks for an MX record, a mail exchange record.
Oh, right, MX records.
The MX record is brilliant because it has priority routing built in. DNS might return 3 different servers for a single domain, number 10, 20, and 30. Your MTA will try the primary server at priority 10.
And if it's down?
If that server's offline, it doesn't fail. It seamlessly falls back to the backup server at priority 20, which will just hold the email until the primary comes back online.
That transfer between servers across the internet happens via SMTP, Simple Mail Transfer Protocol. And SMTP is a push protocol. It aggressively knocks on doors to shove the data forward.
Yep, it's very proactive.
But when the email finally hits the recipient's mail delivery agent, the MDA, the push stops. It just sits in a database. When the recipient wakes up and checks their phone, they aren't using SMTP.
No, they are using a pull protocol like IMAP or POP3. They connect to the server and basically say, what do you have for me? This split architecture, pushing over the internet, pulling to the device, is what enables that asynchronous magic.
Which is so different from POP3 historically, right? POP3 would just download the email and delete it from the server.
Yeah, which was terrible for multiple devices. But IAM revolutionized this by keeping the state synchronized in the cloud, treating the server as the ultimate source of truth, so your phone, tablet, and laptop all show the same read receipts.
Let's talk about the constraints of SMTP, though. When John Postel and the early pioneers designed it in 1982, they designed it for 7-bit ASCII text. Basically just basic English characters.
Very basic.
No attachments, no bold fonts, no foreign alphabets, and definitely no photos or spreadsheets.
They built a system constrained to transmitting data in 7-bit chunks. If you try to send a raw JPEG image, which is compiled of 8-bit binary data through an old SMTP server, the server will literally strip the 8th bit off every byte, completely destroying the file.
It just corrupts it entirely.
Exactly.
So to fix this without rebuilding the entire global infrastructure, they invented MIE, multi-purpose internet mail extensions. I always view MIME as the ultimate backwards compatible hack.
Oh, it really is a hack.
It's like having a physical postal system built exclusively for flat, standard-sized envelopes. And you want to mail a bowling ball, you can't. So you invent a machine that perfectly disintegrates the bowling ball into flat pieces of paper, stuffs them into 1 million standard envelopes, mails them, and the recipient uses a reverse machine to rebuild the bowling ball.
That's hilarious, but it's completely accurate. You're talking about base 64 encoding. MIME takes raw 8-bit binary data, your PDF, your photo, and mathematically translates it into a bloated, inefficient string of standard 7-bit ASCII text characters.
There's a random-looking text.
Yeah, it packs it into the email body, adds headers explaining what the data actually is, and shoves it through the legacy SMTP pipes. The receiving client reads the MIME headers and translates the text back into a visual photograph.
It is brilliant extensibility. But while MIMP solved the media problem, it ignored the existential threat to email, which was trust.
In the 1980s, SMTP servers were polite to a fault. If a server at MIT received an email destined for Stanford, it would cheerfully accept the email and forward it along on behalf of the sender. These were known as open relays.
Which sounds nice in theory.
In a small, high-trust academic community, open relays provide robust, helpful routing around network outages.
But in a global commercial internet, open relays are a weapon of mass destruction. By the late 90s, spammers realized they could connect to any poorly configured server in the world, dump 1 million junk emails into it, and force that innocent server to spend its own bandwidth distributing the spam.
It was a nightmare.
It obfuscated the spammer's origin and nearly brought the internet to its knees.
Closing open relays took a massive, decade-long coordinated effort. Servers were reconfigured to only accept mail destined for their own local users or mail originating from their authenticated local users. But closing the relays didn't solve the core protocol flaw.
Which is?
SMTP has absolutely no mechanism to verify the from address. I can connect to a server, type mailfromceo@yourcompany.com, and the protocol will process it without blinking.
And we circle back to the central theme again. How do you bolt identity and authentication onto an aging open protocol? You use the one distributed database everyone already relies on. You hide security policies inside DNS text records.
Yep, DNS to the rescue again.
The industry built what I call a holy trinity of email authentication: SPF, DKIM, and DMRC. Let's dissect the mechanics, starting with SPF, the Sender Policy Framework.
So SPF is basically a mechanism for IP whitelisting. An organization publishes a DNS record listing the specific IP addresses of the servers authorized to send mail for their domain.
Okay, simple enough.
When the receiving server gets an email, it looks at the IP address of a machine making the connection, queries the DNS SPF record, and checks if there's a match.
It's simple, but it's incredibly brittle, isn't it? If I send an email to a university alumnus address and the university automatically forwards it to their personal Gmail account, the email breaks.
Yes, it breaks completely.
Gmail looks at the incoming connection, sees the IP address of the university's forwarding server, checks my domain's SPF record, sees the university is not on my whitelist, and flags the message as forged. SPF cannot survive the fundamental store and forward nature of email.
Which necessitates the second pillar, DKIM. Domain keys identified mail. This moves the trust away from the IP address and places it onto the message itself using cryptography.
How does that work?
The sending server takes the headers of the email in the body text, runs them through a mathematical hashing algorithm, and signs that hash with a private key. It attaches the signature as a header to the email.
And the public key is published in a DNS text record. So when the receiver gets the email, even if it's been forwarded through 5 different servers, it pulls the public key from DNS, it recalculates the hash of the body.
Right.
If the hashes match, 2 things are mathematically proven. The email genuinely originated from the domain claiming it, and not a single comma in the body has been altered in transit.
DKIM is very elegant, but it still leaves a psychological loophole. A spammer can register, cheap-viagra-deals.com, set up their own server, publish their own SPF records, and sign the emails with their own DKIM keys.
So they passed the test.
Exactly. The spam will technically pass all authentication checks. The spammer then alters the visible header from address, the one the user actually sees in their mail client, to look like support@paypal.com.
Oh, wow.
The underlying technical authentication passes, but the human is completely deceived.
And that is why DMRC was invented. It is the enforcer. DRC forces alignment. It dictates that the domain verified by SPF or DKIM must cryptographically match the domain visible to the end user. If they don't align, the authentication is void.
Yes, it ties it all together.
But DARMR is also a policy layer, right? It tells the receiving server what to do with the failure. You can set the policy to none for monitoring, quarantine to send it to the spam folder, or reject to drop the email at the gateway.
And setting that policy to reject is one of the most perilous IT operations a company can undertake.
Why? I mean, if you want to stop spoofing, shouldn't every company just flip the switch to reject immediately?
Because of shadow IT.
Oh, right.
Large corporations have dozens of third-party platforms sending mail on their behalf. The marketing department buys a new SaaS tool to send newsletters. The HR department uses a cloud provider for payroll stubs. The customer service team uses an automated ticketing system.
They're all sending email as the company.
Exactly. If the IT department doesn't meticulously track down every single one of these external platforms, collect their IP addresses, and configure their DKIM keys before turning DMORART to reject, they will instantly block all of their own legitimate business communications.
The invoices stop sending. The password resets fail. The business just grinds to a halt. It's self-inflicted sabotage.
It's a nightmare for IT.
That's why DMRC includes a reporting feature, sending daily XML digests back to the domain owner so they can hunt down the shadow IT before they drop the hammer.
It is a phenomenal hack, layering complex identity verification over a 1980s protocol. But, all of this cryptographic security, DNS SEC verifying the hierarchy, DKEN Mead signing the email bodies, TLS encrypting the connections, it all rests on a foundation even deeper than DNS.
What's that?
There is a hidden dependency that, if broken, causes the entire cryptographic architecture of the internet to silently implode.
You're talking about time. Every digital signature, every TLS certificate provided to the padlock in your browser possesses a strict validity window. It is valid from this specific second to this specific second.
Yeah.
If your laptop's internal clock drifts by just 5 minutes, the mathematical contracts become void. A perfectly secure connection to your bank will be aggressively terminated because your computer believes the bank certificate hasn't been activated yet, or maybe has already expired.
Time synchronization is not a user interface convenience so you know when to go to lunch. It is critical security infrastructure. But synchronizing clocks over a global network with entirely unpredictable lag is a massive mathematical challenge.
Right. Because how do you know what time it is when the message telling you the time takes an unknown number of milliseconds to reach you?
You use NTP, the Network Time Protocol. And here we see our grand unifying theory again. Hierarchy. NTP organizes time sources into stratums. At the very top, stratum 0, you have devices that do not get their time from a network.
Where do they get it?
They get it from physics. Cesium atomic clocks, GPS satellite receivers, they are the absolute truth. Stratum 1 servers are physically cabled to those Stratum 0 devices. Stratum 2 servers sync to Stratum 1 over the network, expanding the tree, distributing the load, ensuring millions of clients don't crush the atomic clocks.
But the brilliance of NTP lies in the algorithm that runs between a client and a server to calculate the network delay. It doesn't just ask the time, it calculates the transit.
Yeah.
Let's visualize the math here.
Sure.
Imagine we are trying to synchronize our watches, but you're standing across a massive foggy canyon. We can only communicate by yelling, and sound takes time to travel. I yell across the canyon. My watch says it is exactly 12.000000. That is timestamp 1, the origin time.
Okay, I hear your yell. I look at my watch. It says 12.01.00. That is timestamp 2, the receive time. It took some amount of time for your voice to reach me, plus my watch might be fundamentally wrong anyway.
Right.
A moment later, at my 12.02.000 timestamp 3, the transmit time, I yell back, I received your message at my 12.01 and I am replying at my 12.02.
The echo travels back. I hear you reply, look at my watch, and it says 12.04.00. That's timestamp 4. I now have 4 data points from one round trip. I know the total time elapsed on my watch was 4 minutes, from 12.000 to 12.04, but you told me you were only processing the data for 1 minute, from 12.01 to 12.02.
Right.
That means the sound spent exactly 3 minutes in transit through the air. Assuming the wind is identical in both directions, I divide the transit time in half. It took 1.5 minutes to reach you.
So if you yelled at 12.0 and transit took 1.5 minutes, you know it was exactly 12.01.3 time when I heard it. But my watch said 12.01.00, therefore my watch is exactly 30 seconds slow. You calculate the offset and gently slew your system clock to match reality.
It is brilliant in its simplicity. It isolates the transit time and removes it from the equation. But I have to assume the internet is much messier than a foggy canyon.
It is. Your analogy contains a fatal assumption that plagues modern networking. You assumed the wind is identical in both directions. You assumed symmetric delay. NTP's mathematics require the packet to take the exact same amount of time to reach the server as it takes to return. On the internet, this is almost never true due to BGP.
The Border Gateway Protocol.
Right.
Right, because BGP doesn't care about physical distance. It cares about business relationships and AS paths. Asymmetric routing is the norm.
Precisely. The path from your computer to the time server might travel over a direct high-speed peering link, taking maybe 10 milliseconds, but the return path might get routed through a congested transit provider in a different city, taking 50 milliseconds.
Oh, wow.
If you divide a 60 millisecond round trip in half, NTP assumes a 30 millisecond transit. The math is instantly corrupted by the routing asymmetry, biasing the clock offset.
So standard NTP over the open internet will always have a jitter of a few milliseconds. For a web browser checking a TLS certificate, that's fine. But what if you are running a globally distributed database that relies on absolute chronological transaction ordering, or a high-frequency trading firm executing trades in microseconds.
Then you completely abandon NTP over the internet. You install physical GPS antennas on the roof of your data center, dropping stratum zero time directly onto your local network using the Precision Time Protocol, PTP, bypassing the internet's variable latency entirely. You can optimize software protocols infinitely, but you cannot out-engineer the physical speed of light and the realities of fiber optic routing.
Which brings us to the ultimate architectural hurdle. If you have a user in Sydney trying to load a high-resolution image from an origin server in New York, the light and the fiber optic cables takes roughly 80 milliseconds just to travel one way.
And that's just the physical limit.
Right. TCP handshakes and TLS cryptographic negotiations require multiple round trips before a single byte of the image is even requested. Those milliseconds compound. The delay becomes highly visible to the user. You cannot make the light move faster, so you have to cheat physics. You have to change the physical geography of the internet.
This is the advent of the Content Delivery Network, or CDN. It is the planetary scale application of our caching mechanism. If you can't bring the data faster, you bring the data closer.
Makes sense.
You deploy thousands of servers in edge data centers in Sydney, in Tokyo, in London, in Mumbai. When the user in Sydney requests the image, the network hijacks the request and routes it to the server located 2 miles down the road.
The latency collapses from hundreds of milliseconds to single digits. The origin server in New York is radically offloaded, protecting it from being crushed by viral traffic spikes. But the engineering magic here is the steering mechanism. How does my browser actually know to talk to the edge server in Sydney instead of the origin in New York?
The historical method relies on DNS redirection. A website administrator creates a CNAME record, a canonical name alias. They point example.com to the CDN's internal domain name. When your recursive resolver does its iterative walk and hits the CDN's authoritative DNS server, the CDN looks at the IP address of the resolver asking the question.
Okay, I follow.
It runs it through a GeoIP database, figures out the resolver is in Sydney, and hands back the IP address of the Sydney edge cache.
But wait, we discussed this earlier. The authoritative server doesn't see me, the user. It only sees my recursive resolver. If I live in Sydney, but I've configured my laptop to use a public DNS resolver located in California for privacy reasons, the CDN thinks I am in California.
You've identified the massive blind spot in DNS-based steering. The CDN will hand your Sydney laptop the IP address of a California edge server. Every single image you load will cross the Pacific Ocean twice, completely destroying the performance benefits of the CDN.
That defeats the whole purpose.
It does. To mitigate this, engineers developed an extension called EDNS0 Client Subnet, where the resolver attaches a truncated piece of your actual IP address to the query, giving the CDN a hint about your true location. But from a privacy standpoint, leaking your subnet to authoritative servers is highly controversial.
Which is why the modern, more elegant solution for steering traffic doesn't use DNS logic at all. It uses the physical topology of the network itself. It uses Anycast.
Anycast is fascinating. Normally, an IP address is a unique identifier pointing to a single machine on Earth, unicast. But with Anycast, the CDN configures dozens of different data centers across the globe to broadcast the exact same IP address via BGP routing tables.
I picture it like stretching a rubber sheet to represent the internet and dropping heavy bowling balls onto it to represent the data centers broadcasting the Anycast IP. The network routers naturally create topographical gravity wells.
That's a great visual.
Right. When I send a packet to that IP address, the network just rolls the packet down the shortest AS path, automatically dropping it into the geographically closest data center. The user doesn't have to calculate anything.
And that natural gravitational pull provides profound resilience against distributed denial of service attacks.
How so?
If a botnet of 1 million infected IoT devices tries to overwhelm an IP address with a volumetric flood of traffic, a unicast server will be obliterated. But an Anycast IP naturally dilutes the attack. The bots in Europe are pulled into the European data centers. The bots in Asia are absorbed by the Asian caches. The attack is segmented and soaked up locally, preventing any single location from being overwhelmed.
The edge absorbs the blow. And what actually lives at that edge has evolved dramatically, hasn't it? It started as simple object caching holding static JPEGs and CSS files. Then CDNs moved to connection termination, maintaining long-lived, secure TLS sessions with the client at the edge to eliminate the cryptographic handshake latency, even if the request had to be forwarded to the origin.
And today, we're in the era of edge compute. The edge isn't just a dumb hard drive holding files. It is a globally distributed, serverless computing platform. Developers push executable code directly to the edge. Request routing, authentication checks, personalized content generation. It all executes within milliseconds of the user, radically decentralizing application logic.
But despite all that computational power, the vast majority of the raw bandwidth flowing through these CDNs is dedicated to one thing: video.
Oh, yeah, it consumes the internet.
And delivering flawless video streaming to thousands of different devices over fluctuating Wi-Fi and cellular networks requires an architectural paradigm shift. You have to move the intelligence out of the network and into the endpoint.
Exactly. When you watch Netflix or YouTube, you are not using a specialized stateful streaming protocol maintaining a continuous pipe. Adaptive bitrate video like HLS or MPEG- treats video as a series of dumb, static files.
The video file is chopped into tiny fragments, usually 2 to 10 seconds long. And every fragment is encoded at multiple quality levels, from a blurry 360p file for a bad cellular connection, all the way up to a massive 4K file for a hardwired smart TV.
The HTTP server hosting these fragments at the edge is entirely agnostic. It doesn't know it's serving a movie, it doesn't know the bandwidth of the client, it just waits for requests and hands over a file. The intelligence, the decision-making engine, lives entirely within the video player software on your device.
This is the end-to-end principle manifesting beautifully. The core network is dumb and fast, the edge client is smart. The video player has to decide every few seconds which quality level to request for the next fragment. It's constantly analyzing the environment, running an algorithm called adaptive bitrate, or ABR.
The evolution of ABR algorithms is a masterclass in control theory. The first generation used rate-based ABR. The player would measure the time it took to download the previous segment, calculate the TCP throughput, and attempt to forecast the available network bandwidth. If it guessed you had 10 megabits per second of bandwidth, it would request an 8 megabit video segment.
But predicting internet bandwidth is a fool's errand. Throughput is incredibly noisy. You walk behind a concrete wall, or a microwave turns on, or the cellular tower hands you off, and your bandwidth drops by 80% instantly.
It's so unpredictable.
If the rate-based algorithm guesses wrong and asks for a high-quality segment over a suddenly degraded connection, the segment takes too long to arrive. The video player runs out of buffered video, the screen freezes, and you get the spinning wheel of death.
The buffering stall. The ultimate failure metric for a streaming service. To eradicate it, researchers and engineers pivoted to buffer-based ABR. They stopped trying to guess the erratic throughput of the network and instead focused on the one metric the client can measure with absolute certainty: its own internal buffer occupancy.
The logic is basically a step function. The player looks at how many seconds of video it has loaded in memory. If the buffer is full, say, 30 seconds of video ready to play, the player confidently requests the highest possible quality for the next segment. It doesn't matter if the network is fluctuating, because it has a 30-second safety net.
But if the buffer begins to drain, meaning the player is consuming video faster than the network is delivering the new segments, the algorithm reacts instantly. As the buffer drops below certain thresholds, the player aggressively requests lower and lower quality segments. The file sizes shrink, allowing them to download faster over the constrained connection, rebuilding the buffer.
It prioritizes continuous playback over visual fidelity, except that a blurry video is vastly superior to a frozen video. The player treats its own buffer as ground truth, ignoring the noisy network entirely.
It is a profound lesson in systems engineering. The most robust control signals are the ones you can measure directly, not the ones you must infer. Buffer-based algorithms revolutionize streaming reliability precisely because they stop trying to predict the unpredictable.
Now, before we conclude, we must acknowledge the architectural foil to the CDN model. Because while CDNs dominate commercial delivery, they still rely on massive centralized edge servers. The alternative to this is peer-to-peer networking, specifically BitTorrent.
BitTorrent flips the paradigm completely. Instead of deploying expensive servers closer to the users, it turns the users into the infrastructure. When you download a file via BitTorrent, you simultaneously upload the cryptographic pieces you've already received to other peers in the swarm.
It fundamentally reverses the scalability problem. With a centralized server, a massive influx of users causes a bottleneck and the server crashes. With BitTorrent, every new user brings new upload bandwidth. The more popular a file becomes, the faster the network gets. But the true genius of BitTorrent isn't just the chunking of files. It's the game theory woven into the protocol.
The tit-for-tat algorithm. Peer-to-peer networks traditionally suffer from the free rider problem. Users want to download files, but they cap their upload speeds to save bandwidth. BitTorrent solves this economically. The software evaluates the peers connected to you, and it deliberately unchokes or provides upload bandwidth to the specific peers that are currently providing you with the highest download speeds.
It is an algorithmic meritocracy. If you throttle your upload, the swarm detects your lack of contribution, chokes your connection, and your download speeds plummet to dial-up levels. It mathematically aligns individual selfish incentives with the collective health of the distributed system.
It is arguably the most elegant distributed system ever deployed. But CDNs ultimately won the war for commercial media delivery, the Netflixes and Disneys of the world, for three reasons. First, predictability. CDNs offer guaranteed performance backed by service-level agreements regardless of peer availability. Second, legal boundaries. CDNs centralize the hosting of copyrighted material, whereas P2P forces users to legally distribute the content themselves.
And third, the cold start problem. If you release a highly anticipated movie episode, the very first user who hits play on a CDN gets it instantly. In a peer-to-peer swarm, the initial distribution relies entirely on the origin seeders, which takes time to replicate out to the swarm. BitTorrent's architectural DNA lives on in back-end data center replication, but CDNs won the edge.
So we step back and look at the tapestry of this hidden infrastructure. We saw how the DNS graph scales indefinitely through zone delegation and local caching. We saw how email achieves robust asynchronous delivery, relying on DNS to bolt cryptographic identity over an untrusted protocol.
We looked at how NGP uses distributed hierarchy and offset mathematics to fight network delay, providing the chronological foundation for global cryptography. And finally, we saw how CDNs use BGP, Anycast, and edge computing to physically bypass the speed of light, while smart endpoints use control theory to perfectly tune video streams against chaotic network conditions.
They are entirely different protocols, operating at different layers, built decades apart. Yet they survive by adhering to the same grand theory. Partition the workload to prevent central bottlenecks, and cache the reality at the edge to survive failure.
Which leaves us with a vital architectural question to ponder. The entire internet was designed to route around damage, to possess no master switch, and to avoid single points of failure. Yet today, the vast majority of global web traffic flows through a handful of mega CDNs. The vast majority of our encrypted DNS queries are being funneled into the servers of 2 or 3 massive browser and search monopolies via DH. We built a system with no central authority, and then slowly, in the pursuit of speed and encrypted security, we handed the keys back to a centralized oligopoly. The next time you type a domain name and a video loads flawlessly in milliseconds, ask yourself, in a decentralized world, who actually controls the edge?
That is the defining architectural conflict of the modern web.
Until next time, keep diving deep.